Okay, so let's kind of review some stuff from yesterday. So, and this is going to form the basis of what we're going to talk about today. So when you talk about acids and what we can physically measure. So when you look at a pH probe, what you're measuring, and it's written two different ways. Sometimes you'll see it written as a hydronium ion concentration, sometimes you'll see it written as this. So a couple of things about style. When you see anything written with these square brackets, that's talking about a concentration measured in molarity. So no matter, and we're going to see this a whole bunch of different ways. So anytime you see the square brackets, we're talking about concentration, and it's in moles per liter. So one of the kind of basic ideas of this, and where this kind of whole thing starts, is that when you have a solution that has acids and bases in it, hydronium ions and hydroxide ions, and this is what's written on that green sheet. Your hydronium ion concentration times your hydroxide is equal to 1.0 times 10 to the negative 14. Okay, so that's kind of the basic idea where all of this is going to start. So if at any point you know either the hydronium ion concentration or the hydroxide ion concentration, you can figure out what the other one is, because those two numbers multiplied together equal 1.0 times 10 to the negative 14. Now, this is a little bit weird because this doesn't have any units on it. This is just a constant. It's called the auto-ionization of constants, or auto-ionization constant of water. So sometimes you'll also see this written as just your hydronium ion concentration times OH equals that number. These mean the same thing, okay? So don't get confused. Oh, this is one thing, this is another. This is technically more correct because the reason this is more technically correct is because what you have here is a proton, which is a hydrogen without the electron, attached to a water molecule. So if you're a pure chemist going, oh man, I want to do this and have this right, technically this is more correct because this is actually what it is. It's a proton that's attracted to a water. A lot of times we shortcut it and we just put H+, but it means the same thing. So this is the same as this, okay? It means the same thing. They're both hydronium ions. So when you have what we call a neutral solution, any neutral solution, the hydronium ion concentration is the same as your hydroxide ion concentration. So in a neutral solution, these are both 1 times 10 to the negative 7th. Equals 1 times 10 to the negative 14th. Okay, so in a neutral solution, your hydronium ion concentration is the same as your hydroxide ion concentration. So that way when I multiply these two numbers together, I get 1.0 times 10 to the negative 14th. Now, Mother Nature smiled on chemists when Mother Nature decided this number, okay? This could have been so much more complicated. That could have been like 3.72 times 10 to the negative 15th, okay? Which would have made these calculations much more difficult. Mother Nature smiled and said, hey, chemists, I'll take pity on your little pathetic souls. And I'm just going to make that 1.0 times 10 to the negative 14th. That way, when I multiply these two numbers together, oh, that's 1 times 10 to the negative 7, that's 1 times 10 to the negative 7, okay? Now, that forms the basis of the next step. So when you look at pH, okay, and remember, when you see P, P stands for negative log, okay, no matter what. If you have pH, it's the negative log of your hydronium ion concentration. If you have POH, it's the negative log of your hydroxide ion concentration. If you have pKa, it's the negative log of your Ka value, okay? So P, no matter what, stands for negative log, okay? So if you have a neutral solution, if I take the negative log of 1.0 times 10 to the negative 7th, which is my hydronium ion concentration, oddly enough, I get 7.00. Okay? Now, this is why when you have a neutral solution, the pH is 7. Is because you're taking the negative log of 1.0 times 10 to the negative 7. If the autoionization constant of water had been 1.0 times 10 to the negative 12th, you would have been taking the negative log of 1 times 10 to the negative 7th, and the pH, or negative 6, and the pH would be 6. So the only reason it's 7 is because of a mathematical anomaly. Autoionization of constant of water is 1 times 10 to the negative 14. You take the negative log of that, you get 7. Now, if you want to calculate the pOH, okay, so pOH is the negative log of your hydroxide ion concentration. Oh, you're also taking the negative log of 1 times 10 to the negative 7th. So that gets you also 7.00. Okay? So this is why if you take your pH and add that up to your pOH, you always get 14. So if you ever know your pOH or your pH, you can calculate what the other one is because they add up to 14. So when you're doing pH, it's one of the most important things. You always want to put two decimal places to the right of that number, even if they're zeros, okay? You always want to put 2 decimal places out there. You always want to put 2 decimal places out there. Because if you round too much, that's going to screw up your calculations if you try and work backwards. So, there is going to be huge, this is one of the things that you have to understand without giving it a second thought. The two numbers multiplied together equal 1.20 times 10 to the negative 14th. Your pH plus your pOH is 14. And the reason that neutral water has a pH of 7 isn't because, and everybody has this idea, oh, neutral water doesn't have any hydronium ions in it. It does. Neutral water has hydronium ions, and it also has hydroxide ions in it. But they're in an equal value, which is why if you have a solution that's neutral, we're not saying that there's not hydroniums and hydroxides. We're just saying that it's balanced out, okay? They're still there. So if something's acidic, you have a higher concentration of your hydronium ions, which makes the pH less than 7. If it's a basic solution, your pH is above 7. So and on those notes that I gave you all yesterday, if you look at that. So if you look at a pH scale, okay, and here's 7, that's neutral. So anything less than 7 is acidic, and anything above 7 is basic, okay? And the farther away that is, the more basic it is or the more acidic it is. Now, you can theoretically, your pHs generally don't go below 0. Sometimes they can if you have really, really highly concentrated acidic solutions. You can actually have negative pHs, but that's very, very, very rare that happens. Almost all of the stuff that you're going to do is going to be a pH in this like 1 to 14 range, okay? That's where all yours are going to fall. So, does that kind of help everything where we're at? Okay. Now, let's talk about number 12 on the back, okay? Because this is going to this is the whole point of today's lecture. So, if you look at what's happening on number 12, I want to look at 2 different situations. So, I've got a 0.2 molar solution, or 0.02, molar solution of acetic acid. Acetic acid is HC2H3O2. Don't worry about the structure of acetic acid. I'll never make you memorize it. Just the structure of it. So typically, chemists tend to be efficient. So generally how we write the formula for acids is we just put Ha. It's just, what that means is that this is a hydronium ion that's attached to an anion. So HA just takes the place of any generic acid. Okay, it's just like, okay, we're just going to put it as HA. That's it. If we're talking about bases, we put H and then a capital letter B. Okay, so when you see HA, all we're talking about is just an acid. It's some hydronium ion attached to some anion. If you're talking about acetic acid, that anion is C2H3O2 that has a charge of 1 minus. But here's what's going to be important. Your anion has a charge of 1 minus, your hydrogen has a charge of 1 plus. So here's the situation. We're going to look at two different scenarios. Scenario number 1, we have a 0.2 molar solution of hydrochloric acid. Okay, so hydrochloric acid is like the quintessential strong acid. So if you take hydrochloric acid and you put that in water, hydrochloric acid completely ionizes. So in other words, this is like the Tinder app. This is the chemistry Tinder app. Hydrochloric acid looks at this and goes, huh, there's that water molecule. Am I attracted to it or not? Do I sweep right? Do I sweep left? Okay, that's the decision. Because hydrogen is showing up to the dance with chlorine. Okay, the question is that do I ditch the chlorine and go hang out with the water, or do I stay with my date? Okay, now because hydrochloric acid is a strong acid, it sweeps right. Because it sweeps right, okay, this is like Tinder. It's going to sweep right. That means that we're going to shift everything over here, and equilibrium is going to lie to the right. So what's going to happen is that we're going to make hydronium ions, and we're going to have some chlorine ions left over. So this is going to be my reaction. I cannot emphasize this enough. If you don't know what the reaction is, nothing else makes any sense. So you have to understand that reaction. So this reaction is going to take place, and we're going to shift all this over here, because what happens is that the hydrogen is attracted to the chlorine, but not very much. Okay? It's much more attracted to the water than it is to chlorine ion. So it'd be like, imagine you go to prom and you're going as just friends. Okay? So there's enough of a bond that gets you to prom, and you all have seen this, or at dances or any situation. You get to dance, maybe you take some pictures ahead of time, click, click, okay? But as soon as you get to the prom, you're going to ionize. You're going to go hang out with your friends, because your attraction to your friends is more than the attraction to your date, okay? And you go ahead, bless you, and you go where you're most comfortable. This is more comfortable over here, okay? So if this was a strong acid, so we're going to set up a rice chart. You're going to live and die by rice charts, okay? So initially, this is going to start off at 0.02. I don't worry about the water. You never worry about the concentration of water. And you assume that everything over here starts off at 0. So here's the cheese sandwich analogy. So because of the fact that this is a strong acid, all of this is going to ionize. So at equilibrium, this is going to go to 0. So in other words, I'm not going to have any HCl. Okay, this is 0. It's not there. So over here, I have 0.02, 0.02, right? Now, what I can measure with probes, I can't measure chloride ion concentrations. I'm never going to give you a probe that allows you to measure chloride ion concentrations. But we're going to have pH probes which can measure hydronium ion concentrations. So this is what is going to be my hydronium ion concentration. Now that I have this, then I can calculate my pH. So somebody can take out a calculator, because now I know my hydronium ion concentrations. So somebody take the negative log of 0.020 and let me know what you get.
1.6.
What'd you get?
1.699.
So 1.69 or 1.70?
1.99, so 1.7 I guess.
1.70? Okay. Cool. Because I want 2 decimal places to the right. So what this means is that if I gave Adam a solution of 0.02 molar solution of hydrochloric acid, he should be able to take a pH probe, put it in there, and that should be the reading that he gets on that pH probe. Okay? Now, that only works, listen to me, listen to me, listen to me, listen to me. This only works if it's a strong acid, because tender sweeps right, we produce all of those ions over there, and this becomes the concentration of my hydronium ions. But that only works with strong acids, okay? If it's a weak acid, which we'll see in just a second, you can't do that, okay? But with that, got that idea, we're good, we're golden, okay? Now, let's talk about number 12. So now we're going to deal with acetic acid. So the reaction is going to start the same way. I'm going to take, and I'm just going to put this as HA, okay? As technically it's C2H3O2, but I'm just going to put it as HA. And it's still going to try and react with water. And I'm going to have some hydronium ions produced and some anions produced. Okay? So the only difference here is that instead of HCl, I'm just going to put this as a generic HA. Okay, that's the only difference. So this is my reaction. So the beauty of this is every time you have an ionization of an acid, the reaction is the same every time. This never changes. It's always the exact same reaction. Whether this is acetic acid, whether it's nitric acid, whatever it is, okay? This is how this thing is going to go, okay? Do not make this difficult. So there's my reaction. So now I'm going to have this rice chart. This is still going to, that's going to start at 0.200. I don't worry about the water. I don't have to worry about that. And these are going to start off at zeros, okay? So unless you're specifically told differently, these always start at 0. Eventually, when we get into what's called buffered solutions, these won't start at 0. But that's a ways down the road, okay? So unless I tell you anything differently, you assume that these start off at 0, okay? Now, this is a weak acid, so here's the problem. Because it's a weak acid, it doesn't ionize. Only part of it does. So this is like tinder, but they really don't like to ionize. So in this situation, they really like their date. Okay, so they've gone to prom, and they really, really like hanging out with their date. They might ionize a little bit. They might go run over to their friends. Hey, how you doing? Sorry. Okay, then they're going to run back to their friends. Okay. They're not going to stay away very long because they really like their date. So the struggle here is that we don't know how much of that is going to ionize. So what we're going to do is we're going to use a generic X. Okay, we don't know how much it's going to ionize, so we're going to let that just be X. So we're going to go minus X. Okay, it's going to ionize. I just don't know how much of it is going to ionize. So whatever I lose here, so if I subtract X here, what am I going to do over there? I'm going to add X. Okay? I'm going to add X. So then I add X. So this becomes 0.0200 minus X. And this becomes X. And this becomes X. Okay? Good so far. Good. So this is my equilibrium law. So some of this is going to ionize. I don't know how much. So I'm going to lose some of this. But whatever I lose here is what I gain here. Okay? And that's always going to be the same. Whatever you subtract here is whatever you add over there. Okay? As long as everything's in a 1-to-1 ratio, which in this situation it is. Okay? Good so far. Now, here's the deal. Now, forget that that exists for just a second. We're going to get back to it. So if you look on your equation sheet, you have this calculation of Ka. And this Ka, and this is what's written on your sheet, is notice that that's your hydronium ion concentration times your anion concentration divided by Ha. Okay, so you have H times A divided by Ha. Now, here's one of the most important things to get. Anytime you see this value of K, right? Anytime you see K, the only time in chemistry we use K is on a very unique situation where everything is in equilibrium. So whether that's Ka, whether it's Kb, whatever it is, okay? KSP, we'll do a whole bunch of different K values. But the one thing that's always true, when you see an uppercase K, that means that you're in equilibrium, okay? If we're not in equilibrium, we use a different variable. But here's the beauty, this is in K. Mother Nature likes to be in equilibrium. Now, if you look in, let me see some of this stuff. If you look in the back of your book, back here there's this appendix. And on page 1092, okay, there's a chart of Ka values, okay? And it's arranged in alphabetically based upon the name of the acid. So if you look at that Ka value, every Ka value that's listed there is of a weak acid, okay? So if you're into like little post-it notes or whatever, you're going to be using that chart a lot, okay? So if you want to put like a little piece of paper in there so you don't have to thumb through it, you're going to be using that value, that chart a lot. You'll notice that Ka values, some of them are like maybe 10 to the negative fifth, some of them are much smaller, like 10 to the negative 12, okay? The numbers change depending upon the acid. So here's the deal. And this is what you have to understand. So in this situation, you have acetic acid, and the Ka is 1.8 times 10 to the negative fifth. So let me explain the significance of this number. So what this means is that Mother Nature, when Mother Nature's chilled out and in equilibrium, if you take the hydronium ion concentration times your anion concentration divided by the concentration of the acid at equilibrium, mathematically, Mother Nature is going to do whatever it has to do to get it to equal this number, because that's when Mother Nature is most chilled out, okay? This puts her in her hookah zone, okay? At this point, she's got 1.8 times 10 to the negative fifth. She's like chilled out going, whew, that's good, okay? She's chilled out at this point. If it doesn't equal this, Mother Nature is going to flip out until she gets to this point, because this is the lowest possible energy state. So Mother Nature wants this combination of hydroniums times anions divided by the concentration of the acid at equilibrium to equal this number. Now, if it's a different acid, it's a different number, okay? So here's the deal. So in this situation, this is what we want this to equal, 1.8 times 10 to the negative fifth. So what we're going to do, we can go, okay, I know what my Ka value is because I gave you that number. You've got that. So now we're going to jump up to this situation. I don't know what my hydronium ion concentration is. I'm just going to let that be X. Okay? There you go. Here's my anion concentration. That's also X. So I have X and I have X. Now, let's talk about this. At equilibrium, this is 0.0200 minus X. So technically, we should put this down here at equilibrium. We should put that as 0.02 minus X. But we're going to take a little mathematical shortcut. unless I explicitly tell you otherwise, and I mean I would explicitly tell you otherwise, you just don't worry about that X, okay? Because what we're going to assume is that this is going to ionize such a small amount that it's not, technically we're going to subtract it, but it's not going to change that value. So it would be like you're going to the ocean and you're going to take a cup, and you're going to take a cup and you're going to take water out of the ocean. Technically, did you reduce the volume of the ocean? Yes. Enough to make any difference? No. Okay? So unless I explicitly tell you, and I mean I will tell you in the problem, oh, this is significant and you have to worry about X, you don't worry about X. You just assume that it doesn't change this concentration of crystal. Technically, it's known as the 5% rule, which we'll talk about later. So, what we're going to do on this problem is that we're going to assume that this is X, and this is 0.02, which is the concentration of that acid. So, you have 1.8 times 10 to the negative fifth. Now, when I take X times X, what do I get? 2X or X squared?
X squared.
You get X squared divided by 0.02. So, here's the question. How am I going to get X by itself? Multiply and then do what? Take the square root of it. So, somebody do that. Take 1.8 times 10 to the negative fifth times 0.02, and then take the square root of that.
6 times 10 to the negative 4.
Okay? It's exactly 6.
Yeah.
Okay, 6.0 times 10 to the negative 4. Now, let me tell you what that number means. Because if you don't know what the number means, there's no point in getting the number. So what that number tells me is that that's the concentration of my hydronium ions. That's also the concentration of my anions. So now I have both of these numbers. Okay? Now I know what these are. It's a long haul. So, I still don't have my pH. But, I know what my hydronium ion concentration is. So now that I know my hydronium ion concentration, how can I find my pH? Huh? Fantastic. Was this like gray, black sweatshirt day? I didn't get the memo. You didn't get the memo. Peace out. Yeah, it must be the hair color. Maybe that's it.
Yes, of course.
Okay. So what do you get?
3.22.
3 point what?
22.
3.22. Now, now here's what I want you to look at. Here's what I want you to look at. So this is one of the most important comparisons that we're going to make. So I want you to jump back. We're going to jump way back up here. If we had a 0.02 molar solution of hydrochloric acid, we had a pH of 1.70 because we had a concentration of our hydronium ion concentration of 0.02. Okay? So if it was a strong acid, tender sweeps right, it all ionizes, we have a huge concentration of hydronium ions. Okay? Because Mother Nature is most stable if you have a strong acid. Tender sweeps right, we're over here. Okay? And this is how this is going to exist. You show up to the prom with your date, but you're not going to stay with your date. You're going to go hang out with water molecules. Okay? So you go, whoop, sweep right. If it's a weak acid, which most are, here's what's going to happen. You are going to have an attraction to the water molecules, right? But guess what? You're going to sweep left. You're going to spend much more time over here with your date than you are over here on this side. So this is chemistry tender. If it's a strong acid, which direction do you sweep? Right. If it's a weak acid, you sweep left. Okay? So if it's a weak acid, we say equilibrium lies to the left. If it's a strong acid, equilibrium lies to the right. Okay? So because this is a weak acid, this is why I have to go through this process. If it's a strong acid, hey, it's just going to be whatever that concentration is. So that's what you have to understand. And here, and the reason this happens, okay, and this is what you have to get. The reason that it happens is because if you have a weak acid, it's much more stable in the molecular form than it is in the ionized form. So this might, I'm not saying that this thing doesn't ionize, it does. But at any given instant, this is such a small amount that it's mostly existing as the molecular form of the acid. So if this is in terms of prom, you might go over, say hi to your friends, take a quick selfie, hi, and then you're going to go back to your date. If it's a strong acid, you're going to spend all the time with your friends, and you're not going to be with your date. Yes, ma'am?
Does this work the same with like bases, with weak bases? Like you would just use the...
If it's a weak base or a strong base, it works the exact same way. But instead of producing hydronium ions, you produce hydroxide ions.
And then the anion will be a cation?
Yes, exactly. Exactly. Okay, yes, ma'am?
If we do it with the weak bases, would it still be pH or would it
No,
be
that then you deal with KB and you would deal with POH. But we'll get to that later. Okay, that's late next week. Okay, that's late next week. Okay, now then it says you want to find the percent of ionization. Okay, so to get your percent of ionization is your hydronium ion concentration divided by the concentration of the acid. So in this situation, I'm going to take 6.0 times 10 to the negative fourth, divide that by the concentration of my acid, which is 0.02, and then multiply that by 100 because I want it as a percent. So what do you get?
3%.
3%. Okay? So if it was a strong acid, this would be 100%, or like 99.99%, okay? But since it's a weak acid, it's 3%. So what this means, in terms of a date, you're going to spend 3% of your time away from your date. You're going to spend 97% of the time with your date, okay? So in terms of human interactions, if you consider 100 minutes, you're going to spend 100 minutes at prom. 3 minutes you're going to spend with your friends. You're going to spend 97 minutes with your date. Okay? Got that? Now, if you're a strong acid, you're going to spend 100 minutes with your date, away from your date, and no time with your date, or at least very little. You might step back by, hi honey, how you doing? Okay, there I go. Okay? Might do like a drive-by, how you doing? Okay? Cool with that. We'll spend more time talking about that, but that's going to be, you're going to do this calculation a lot. Okay? You're going to do this calculation a lot. Okay. Good with that. Okay. Now, let's talk about number 13. So number 13, here's what you're trying to figure out. You're trying to figure out the ratio of nitrogen to oxygen. So let me back up just a little bit, okay? Let's talk about a compound that you know. Pretty familiar with compound water, H2O, right? So when you see H2O, what does that mean?
2 hydrogens are bonded.
2 hydrogen what?
Ions?
Grams, atoms, neutrons, atoms. So this says we have 2 hydrogen atoms that are bound to every 1 oxygen atom. That's what that means, right? Now here's my question. If I multiplied everything by 1,000 and said, I'm going to have H2000 O1000. Is that still the same ratio of hydrogen to oxygen? Okay, it is. If I could go 2 million, 1 million, doesn't make any difference, right? So could I do this? Could I take H times Avogadro's number of 6.02 times 10 to the 23rd and O 6.02 times 10 to the 23rd? Would that still be in the exact same ratio? Yeah. But here's the deal. This is what we talked about yesterday. If I have 6.02 times 10 to the 23rd oxygen atoms, how many moles do I have? 1. If I have 2 times 6.02 times 10 to the 23rd hydrogen atoms, how many moles do I have? 2. So here's the whole kicker. When you see a chemical formula, it's a ratio of actually two things. It's a ratio of atoms, 2 to 1, but it's also a ratio of moles. This also says that, hey, 2 moles of hydrogen is going to react with 1 mole of oxygen, okay? But what it is not, okay, listen to me, this, what it is not a ratio of mass. It is not 2 grams of hydrogen to 1 gram of oxygen, okay? So when you see a chemical formula, it is a ratio of 2 things. It's either a ratio of number of particles or it's a ratio of moles, but it is not a ratio of mass, okay? Only 2 options, particles, moles, that's it. Pick one. So what's happening on number 13 is that if you look at how we do, the history of how we do chemistry, chemistry kind of has a jacked up past because chemistry actually started as alchemy. And alchemy, this is like in the kind of the Dark Ages. So kings would employ alchemists to try and find a way to take base metals of like iron and lead and change it into gold. So that's kind of where alchemy, quote, got its start. Okay? So you would go to the king and say, hi, I'm an alchemist. Okay, great. Here's some research money. Find a way to take this pile of lead and change it into gold. That was their job. So alchemists were their first chemists, and this is well before we had the periodic table or anything like that. And so that's kind of where the word chemistry gets its name. It comes from alchemy, okay? So at the time they had no structure, they had no knowledge of protons, electrons, neutrons, or whatever, okay? They would just do these reactions and try and figure stuff out. So once they figured out the concept of the mole, they said, oh, okay, right. If you look at what they could do, they could not ever take a water molecule, and we still can't. We still can't take a water molecule, put it underneath a microscope, look at it and go, oh, there it is. There's just 2 little hydrogen atoms and an oxygen, and they're labeled H and O. No, okay, you can't do that. So what they did is that they'd take these chemicals and they'd split them up. They'd find a way to split them up. Maybe they'd heat them up, maybe they'd run electricity through them, whatever they would do. But they'd find a way to take these constituents and break it apart. So it's like you guys, and I won't do this, but let's say, okay, I've got the 7 of you, and I want to figure out, hey, what percentage of you are males, what percentage of you are females? What percentage of are wearing black hoodies, what percentage of you are wearing a green sweater, okay? But what I'm going to do is I'm going to break you all apart by some criteria and say, okay, hey, here's the percentage of this, here's the percentage of that, okay? So basically what happened on number 13 is that an alchemist was given this compound that contained nitrogen and oxygen, okay? They said, oh, what's the percentage? Oh, okay. So maybe they heated it up and they collected the oxygen or they collected the nitrogen. Somehow or another they split this up into its constituent parts. It would be like me splitting you up. Like, okay, hey, I'm going to split it down here. You all go over here, you all go over here. By some method, we're going to split this thing apart. And you collect the data and you say, hey, based upon these numbers, on number 13, you're told that it's 25.9% nitrogen and it's 74.1% oxygen. Oh, okay, so that's the first step. Somehow or another, we split this thing up, and these are the numbers that we found out. Oh, right, how do we use that to make a formula? So this is where you go back to the idea that the formula is a ratio of moles. It's not a ratio of mass. It's not a ratio of percentages. So the great unifying theme is that we change these into moles. So the easiest thing to do, and I don't care what, you could assume that you have 0.259 grams of nitrogen and 0.741. I just say, hey, I got a 100-gram sample, I got 25.9 grams of nitrogen, I got 74.1 grams of oxygen, okay? That's the easiest way to do the problem. So you can take 25.9 grams of nitrogen, and you're going to change that into moles. Now, you're not specifically told this is like nitrogen gas. If it was nitrogen gas, you'd use N2. But you're just told that it's nitrogen, okay? So what's the molar mass of nitrogen? 14.0 grams, and that's 1 mole. So out of this, you're going to get, what is that, 1.85 moles of nitrogen. Now, when you do this process, certainly don't round this too much. If there's ever a step in chemistry where you keep more digits than you're going to need, it's a process like this. So don't round this to like 2. Okay, it's going to be a train wreck. At a minimum, you want to keep this as like 1.85. Okay, don't round this step too much. Keep that as 1.85. Then you're going to do the same thing with the oxygen. So you've got 74.1 grams of oxygen. Molar mass of oxygen is 16. That's 1 mole. You get 4.631. Okay. Now, here's the big picture. Here's the big picture. Here's the big picture. You're trying to find this ratio of nitrogen to oxygen. You're trying to figure out what subscripts go down there. That's what you're ultimately after. That's the big idea. So here's the deal. At this point, just step back. Alan, what's going to be the bigger number, my nitrogen or my oxygen?
Oxygen,
Why?
because it's bigger.
Yeah, I have more moles of oxygen. Okay? So I know when I get done here, my coefficient on my oxygen, chemistry clap? Nice. So instead of a golf clap, it's a chemistry clap. So I know when I get done, my oxygen coefficient here has to be bigger than my nitrogen coefficient. Okay? It's a simple thing, but just step back and go, oh yeah, right, this is the bigger number. Yeah, I gotta have a bigger number there. So this is a ratio, right? So at this point, take big divided by small. So we're going to take 1.85 moles of nitrogen, and we're going to divide that. So what's going to be important is that this is going to be a ratio, okay? This is going to be a ratio. So when you take 4.631 and divide it by 1.85, what do you get? 2 point what?
It's like 2.5.
2.5. Okay. Now, we can't round that. That's too far away to round up to 3 or to round down to 2. Okay? We got 2.5. But the problem is we can't have 2.5 oxygen atoms. It's awkward. It's like, because we can't have like 2 and then, oh, we're taking an oxygen atom and split it in half. It's like, no. It's like, what's the average class size in Mays High School? 18.5. Okay, who's going to be that half student? You know, we're going to divide one, cut one in half? Okay, you get half, I get the other half. Okay? No. So we can't have 2.5. So, but, here's the trick. We got 2.5, which is, I can just write as a fraction. So Morgan, what's 2.5 as an improper fraction?
5/2.
5/2. Oh, now that's something I can work with. Okay? So this means that I have 5 moles of oxygen to 2 moles of nitrogen. So what's the chemical formula then? N2O5.
5.
I've never seen that.
Well, you've never been in an AP chemistry
Well,
class.
it's like, I don't know, Miss I just told us like we had rules, so it's like if it's like 0.7 or 8, you would like multiply by 3. Do you know what I mean?
No.
Oh. So like we would do the 1.85 that we got from, we would do all the like elements, you divide by the smallest number.
Yeah, which was the 1.85.
Yeah, so then you would get 1 and then 2.5. And then since it's a 0.5, you multiply everything by 2. So then you get 1 times 2, there's 2 nitrogens. And then 2.5 times 2 is 5.
It's the same thing.
Yeah. But does that work for everything? What happens when you have like 3 elements?
It would be the same thing.
It would. Oh,
Yeah.
you have to do the biggest one though?
Yeah, you still divide by the smallest number.
Okay.
Yeah. So yeah, so now here's how you can, how can you check that you got this right? How can you check that this is right?
Take a percent of it. Like,
Yeah, work
add it
backwards.
up.
Take N2O5, find the molar mass of N2O5, divide the mass of oxygen by the total mass, see if you get that percentage of oxygen. Find the mass of your nitrogens, divide that by the total mass, see if you get the percentage of nitrogen. That's how you can tell if you got it right. Okay? All right, anything else on that review? Going once, going twice. So when you guys hand stuff in, it's that second tray down. Kira, that's going to be old hat for you because Morgan and Adam, you're going to have a little bit of a struggle because you're always going to try and hand stuff into the bottom tray. So anyway, so yeah, so you get that hand, you have to put that in the second tray down. So Morgan, stop that. I didn't get something to drink. So the Arrhenius definition is what I call like the Chem 1 definition of acids and bases. It's the simplest and it works, okay? So on the Arrhenius definition, acids starts with an H, hydrochloric, nitric, hydrobromic, acetic acid. Doesn't make any difference if it's strong acid, weak acid, doesn't make any difference. Acids have hydrogens in them, okay? Bases contain hydroxides. Lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide. Without doubt, the one we're going to deal with most in this class is going to be sodium hydroxide. That is without doubt the most common base that we're going to deal with is sodium hydroxide. So, and it works, okay? And for a while they were cool with this idea. Now, you also have to understand the time frame when this definition came out. At the time, they were still working off of Dalton's atomic theory. Dalton's atomic theory said that the atom was the smallest particle that existed in the universe. They didn't know anything about protons, electrons, neutrons, none of that. Okay, quarks, nothing. So this was a good definition based upon what they knew about the structure of matter at the time. They said, oh, it contains this element hydrogen. Cool. Okay. These contain these elements of OH groups. Okay, that was a common thing. Bases tend to feel slick, okay, kind of like soap. So if you were just given like a solution and all you could do is just like feel and put them on your hands and rub them together, your bases will feel slick. Okay? Now don't do the taste test either. I'll taste it. No, bad. Okay? But if you could just like rub your hands, the bases kind of feel like soaps. Okay? And this definition worked well. It was a very basic idea, but it was a good working definition. But then the problem is that they started to come up and see reactions where you had acid-base reactions that didn't involve your classic idea of hydroxides or hydroniums. So the next one that came along is what's known as the Bronsted Lowry definition. Lowry. Okay, so the Bronsted Lowry, this definition obviously had to come out after they figured out the structure of the atom, where we had protons, electrons, and neutrons. So the other thing about the Arrhenius definition, the Arrhenius definition was limited to only aqueous solutions. Okay, so the classic way that Arrhenius reaction would take place is that, let's say that you had hydrochloric acid, and that would have to be a solution, and you would react that with sodium hydroxide, and you would get water and sodium hydroxide. Okay? Excuse me, and sodium chloride, my bad. Okay? So in Arrhenius reaction of an acid base, you always get two things. You get water and you get a salt. So this is like the classic definition. So if you had equal number of moles of hydrochloric acid and neutralized that with sodium hydroxide, you would get salt water. Okay, literally, that's what you would get. You would get salt water. Now, and this is cool and it worked, but it was limited, because you could only deal with solutions. The Bronsted Lowry definition was much broader. And what you'll see is that this actually worked with gases as well. Okay? So this was cool, pretty limited. So this is what I call like the Chem 2/AP Chem definition of acid bases. So this becomes a wider idea. So let me go through some simple examples. So let's say that we're going to take hydrochloric acid, and we're going to put that in with water. Okay? So hydrochloric acid is a strong acid, right? So what are you going to get out of this? H3O, you're going to get hydronium ions and fluoride ions, right? Okay? So, in the Bronsted Lowry definition, this is my acid because it's going to donate a proton to the water. The water is going to be the base because it's going to accept that proton and become H3O+. So this is a situation where you had an acid-base reaction, but this isn't your classic base. This isn't like lithium hydroxide or sodium hydroxide. This is water, okay? So in this situation, water is going to act as a base. And you'll think, oh, you usually don't think of water as acting as a base, but in this case it is. So in this situation, the HCl is the acid, the water is the base. Now, the other thing that comes out of Bronsted Lowry is that you create what's known as conjugate bases and conjugate acids. Okay? So you have an acid base, then you also have a conjugate acid and a conjugate base. So this is, and I'll show you how you know this in just a second. So this is my conjugate acid, and that's my conjugate base. So here's how you can figure out what the conjugate acid is. If you want to figure out what the conjugate acid is, figure out which one would have to give up a proton to get back to where you started. So if you reverse this, this would have to act as an acid because it would have to give off that proton to get back to being water. This would have to act as a base. It would have to take in that proton to get back to being HCl. So with Arrhenius, you never have to worry about conjugate acid, conjugate bases. You only have to worry about conjugate acids and conjugate bases when you have Bronsted Lowry acids and bases. So you're always going to have an acid and base. You're always going to generate a conjugate acid and a conjugate base because of the fact that you're going to regenerate that, and it's going to go back. This is going to act like an acid, and it's going to go back to being this to the water. This is going to act as a base because it's going to be going back to HCl. So you're always going to have a conjugate acid. You're always going to have a conjugate base. So if you look at Nh3 and water. So, and we'll do this demo next week. So this is ammonia. So one of the things you have to keep straight is the difference between ammonium and ammonia. Ammonia is NH3. It's a gas. This is ammonium, which is NH4 with a charge of 1+. So how this happens is that you take water, you generate ammonia by heating up a solution that contains that. It turns it into a gas. And then you bubble that into the water and you get this reaction. So this is OH. Oh, I screwed that up. This is OH, not Cl. I can't believe I did that. There's a big difference. Oh, don't want to highlight it. Oh, come on. Erase. Okay. So what happens here is that this NH3, right, comes along to the water and says, hey, give me one of your protons. So in this situation, water takes a hydronium ion and becomes H3O. In this situation, water actually gives up a proton and turns into NH4 and hydroxides. So in this situation, water is acting as the acid, and the NH3 is acting as the base. So here's the question. Is NH4, ammonium, is this my conjugate acid, or is this my conjugate base?
Isn't it conjugate acid?
Conjugate acid, why?
Because it has to donate in order to become...
Yeah, it has to donate a proton to get back to being NH3. So this is your conjugate acid, and this is your conjugate base.
Is it only water that can do that, or
It's one of very few. So water is said to be what's called amphoteric. Okay, water is amphoteric in the sense that it can act as an acid or a base depending upon the situation. Okay, and water is one of the very unique chemicals that can do that. It's the most common. So here's what I want you to see: is that in this situation, water acts as a base. It takes a proton from the HCl and you create chloride ions. So in this situation, the solution is going to become acidic because we're generating hydronium ions. In this situation, the water is going to become basic because we're generating excess hydroxide ions. So this one would cause the pH to go down because you're generating hydronium ions. This one is going to make the pH go up because you're generating hydroxide ions. So this is a situation where you have an acid-base reaction, but you don't have the classic, oh, hydrochloric acid. You have ammonia, okay, and you have water. So this is why the Bronsted Lowry is a broader idea that you can use as opposed to just the strict definition of hydrochloric acid and sodium hydroxide, okay? So this is a broader idea. This also works with your classic ones of hydrochloric acid and HCl. So even on a Bronsted Lowry, if you look at what happens with hydrochloric acid and sodium hydroxide, hydroxide here acts as a base because it's going to take in that proton and make the water. You get sodium chloride here as a byproduct. So here's here's what you have to get. When you look at this Bronsted Lowry, in terms of what's going to happen, if you want to figure out the conjugate acid, take the structure, add a hydronium ion to it, increase the oxidation state by 1. If you want to figure out what the base is, take whatever the structure is, take away a hydrogen, reduce that oxidation number by 1. Okay, that's the simplest thing. Because a lot of times they'll say, oh, here's the base, write the conjugate acid, or here's the acid, write the conjugate base. So you either add a proton or subtract a proton. Okay, so we got all of that. How much time we got? Okay, so when you look at your, what time do you guys need to leave?
3 more minutes, maybe?
Huh?
3 more minutes around?
Okay, all right. I'm going to make this quick. Okay, so here's the deal. So let's say that you're comparing two different acids. Acid number 1 has a Ka value of 1.0 times 10 to the negative 5th. The second acid has a value of 1.8 times 10 to the negative 8th. They're both going to calculate the Ka value the exact same way. Okay? But here's the deal. This is a much smaller Ka value than this one is. So don't look at that 8 and go, oh, that's bigger because that's an 8. It's a smaller number because that's 10 to the negative 8th. So if you're comparing these values, if you look at how Ka is calculated, this one has a smaller Ka value. That's 10 to the negative 8th. So what that means is that these numbers here are smaller than to produce this 1.0 times 10 to the negative 8th than it is to produce the 1.0 times 10 to the negative 5th. So when you're looking down that chart of Ka values, the smaller the Ka value is, the less it ionizes. Because to mathematically produce a smaller number, you have smaller values up here. So the smaller the Ka value is, the weaker the acid. Okay, so stop that for a second while I hand out the assignment. Here's back to what you've got. Up here, all this is just basically a summary of everything that we've talked about so far. Okay. Then you've got questions to be answered, and you also have problems from your book. Now, for those of you that are new to me, when you do an assignment, treat this like a textbook. Don't write on this page. So here's your sheet of notebook paper. So if you have to do a mathematical calculation, you're going to draw a line about 1 inch across. So over here, this is where you're going to put your numeric answers. You're going to show the work that goes with it over here. So, and keep these separate. Keep this answer right beside this work. If, like a lot of these have multiple parts, so let's say here's part A, here's your answer, here's going to be the work. Part B, here's that answer, put that work here. In other words, don't put like all your answers up here and then have your work spread out down here. So keep that work right beside that answer. So I should be able to transition from this answer over to that work. Here's this answer, here's that work. Leave spaces in between these things so that it makes it easy for me to grade. Okay, now we're done.